boring. Welcome back to the first details video about the Melexis MLX90363 Triaxis, which is the trademark magnetometer. 2 weeks ago we had a look at the basics of that thing and we got it up and running with an Arduino Nano V3. However, we didn't get much further because there's not a lot of code out there for the Arduino environment supporting the MLX90363 card here. Link in the description. So today we will first do a deep dive into the SPI communication of the MLX90363 and then start with a basic framework for an Arduino library supporting the chip. And we will implement one command and one command only, basically a no command, the NOP command. No operation. So this will all be a bit bland and boring, but it has to be done. Enjoy! Let's dive right into the general message structure that thing uses. We already know from the basics video that obviously in each SPI transactions 8 bytes are transmitted from the master to the slave, and of course it's SPI, 8 bytes come back from the slave to the master. And the bytes are, in general, organized like that. And I have to say, I don't like the way they drawn these diagrams here, because they can trip you up. You see byte 0, which is transmitted first, is here, and byte 7, transmitted last, is here. So really the order of bytes in this diagram is byte 0, 1, 2, 3, 4, 5, 6, 7. So the CRC is really the last byte in the transmission. And just looking at that from a distance, you might think, yeah, it's the byte before the last. But it's really the last byte. Then we have in byte 6 a 2-bit marker and then something they call an OpCode or roll counter, 6-bit. Now, if these 6 bits here are actually an opcode or a roll counter depends first on the 2 bits of the marker and second the direction of the communication. So are these 8 bytes going from the master to the slave or from the slave to the master? Before we have a deeper look in that marker and opcode and roll counter business, let's get the CRC stuff out of the way. This is not your usual CRC that you find in most chips. It's a CRC8 polynomial. In that case, there are 265 CRC8 polynomials, the C2 polynomial. And if you have a table where the polynomial is already calculated, you calculate the CRC simply like that. So you start off with a constant and then you take your first byte and exclusive OR it with your start CRC, and with that, a value between 0 and 265, you go into your 265 byte big CRC table that gives you the next CRC value, and then you continue through the first 7 bytes of the message, and then you have your CRC, which you negate, and that you can write then into your 8th byte of the message. Or in other cases, you calculated the CRC for the first 7 bytes, and then you compare that to the 8th byte in the message. That table is also given in the datasheet in a form like that. I think row is, a line is 20, you know, 20 bytes, and then, it goes down, and it's in a PDF, and it's a normal PDF table. You cannot really do something with it. Fortunately, there is also a getting started application note for the MLX90363, link in the description, where you can simply copy and paste that array into your own code. The question arises, of course, why that array and not calculating that stuff on the fly? If you go to the link in the description to a nice website explaining the CRC8 polynomial, you see right away that, for example, worst case calculating that last value, you need to go to loop 2048 times and do some bit banging, of course. So yeah, it's quite a computational effort to come up with that table. So it's more efficient in terms of speed to store it in an array. Of course, when we're talking microcontrollers here, especially like my old Arduino Nano V3, who has only 1K of RAM, that's 265 bytes, so a 25% chunk of the total memory available. But alas, newer nanos, the Nano Everys, they have a little bit more RAM, so that's not really critical. And here's the method for calculating the CRC of our message bytes 0 to 6, which I will use in my MLX90363 class. And of course, that will return an unsigned integer 8, also known as byte. So first we have here that big 256 byte array. I call it a CRC polynomial, and it's a constant expression here because that makes things a little bit faster, depends on the compiler. And then we just have here our 256 values. That's it. Next, we have two variables here. I'm using the CRC value itself. That's basically the code snippet we just saw in the data sheet. And an I for a loop. We initialize the CRC value to hexadecimal FF. That's a little bit unusual. If you take a look at the article I linked, it's usually initialized with 0. But anyway, they do it this way, so we do it this way. Then I loop through my 7 bytes. I have a constant. We will look at that later. Message size, which is of course 8, because we're always transmitting 8 bytes. So the loop goes through the first 7 bytes. And then I calculate the CRC value as we have seen in the datasheet. So the current CRC value XORed with the message byte we are just processing, that as an index into the CRC polynomial array gives us the new CRC value. And at the end, we just say CRC value is a binary not CRC value, sorry, and we return that. That's it. Let's return now to byte 6, which contains as the two most significant bits the marker, and as the 6 least significant bits either a roll counter or an opcode. Now, there are 3 types of messages which are called by Melexis regular messages, and these are indicated by bit patterns 00, 01, and 10 in the marker position. If such a message goes from the master to the slave, then the 6 least significant bits will contain an opcode. If the message goes in the opposite direction from the slave to the master, then the 6 least significant bits will contain a roll counter. However, there are also not regular messages, and then the marker bit pattern is 1, 1, and the 6 least significant bits will always, independent of the direction of the message, contain an opcode. In the private part of my class definition, I modeled the marker as a enum class, 8-bit, and there we find here the alpha bit pattern 0, 0 for regular alpha diagnostic message, 0, 1 for regular alpha beta diagnostic message, 1, 0 for regular XYZ diagnostic message, and then for all other messages, the 1, 1. Moving on to the opcodes. There's a nice table here inside the datasheet. It misses some information which I added. So basically the left side, and they mentioned that here, that's all the opcodes for the MOSI message. So going from the master to the slave. That is commands. And on the right side, we have the opcodes for the MISO messages. That is just identifying what data the client, slave, is sending back to the master. Then above that red line, these are all the opcodes for the regular messages. And below the red line, there are the opcodes for the other, that is the non-regular messages. And you spotted perhaps that I lied to you. There is a single opcode here for a regular message that can go back from the slave to the master. Anyway, we will talk about all these opcodes in future videos in detail. Today we just want to handle that opcode here, MOSI hexadecimal 10 for a NOP, no operation, and the opcode hexadecimal 11 that comes back as a reply from the slave to the master. Also, yeah, challenge NOP MISO package, or whatever you want to call it. In the private part of our class, I modeled the MOSI opcodes and the MISO opcodes just as enum classes with the type unsigned integer 8-bit. We are just using 6 bits, okay, but yeah, that's the best you can do. And for now, they only contain one member, not for MOSI, the hexadecimal 10, and for MISO, the hexadecimal 11. Next up, of course, are the NOP messages themselves we want to implement. That's a page from the Getting Started guide, by the way, because in the datasheet there's the same information, but these tables are on different pages. So here we have them on one page. So the NOP MOSI, so from the master to the slave message, is mostly empty. Byte 0, 1, 4, and 5. Remember the odd numbering in these tables. But here in byte 2 and 3, we have a key. That can be a random 16-bit number that you transmit over to your slave. And then, of course, the last byte, as always in all messages, is the 8-bit CRC. And here in the byte before the last, byte 6, we have as marker 1, 1. It's not a regular message, an other message, and the opcode hexadecimal 10. And to that message, the slave replies with that data package here, so the NOP MISO message structure, and it simply echoes the key in bytes 2 and 3, and then echoes the binary inverted key in bytes 4 and 5. Byte 7, of course, also contains the CRC, and byte 6, again the marker 1, 1, it's another message. so a non-regular message, and the opcode is hexadecimal 11. How can we model that in an elegant and computational efficient way in software? Let's first summarize what we know so far. In general, a message consists of 8 bytes, 0 to 7. And we know that all MOSI messages, so going from the master to the slave, have in byte 6 the marker and the opcode, and in byte 7 the CRC. We also know that the MOSI NOP messages have in byte 2 the key least significant byte, not bit, byte, and in byte 3 the most significant byte of the key. And then, of course, byte 6 and 7 is again marker, opcode, and CRC. We know that all MISO messages from the slave to the master have in byte 7 the CRC, and that the other MISO messages that are not regular messages, not my terminology, sorry, have in byte 6 the marker and opcode. And the MISO NOP message has in byte 2 the key echo LSB, in byte 3 the key echo MSB, byte 4 inverted key echo LSB, and in byte 5 the inverted echo MSB. And then the rest is the same for all other MISO messages and all MISO messages in general. Another important piece of information is that our little ATmega is a little Indian processor, meaning if you have multi-byte words, like for example the 2-byte 16-bit integers here, the least significant byte is stored at the lowest address. And that's the case here if we think this as our memory, the 8 bytes. The solution I came up with is to use C++ unions. C++ unions have, like C++ structs, members. The difference to a struct is that each member in a struct has its own memory allocated, while the members of a C++ union are all residing in the same memory. That is, you can only use one of the members of a union at a time. Please note that if you switch between the different members of a union, the memory is not erased or reinitialized. So the raw bit data content in the memory from the previously used member is still there. So we could, for example, create a union MOSI message with 3 members. First member being an array bytes with 8 bytes, then a member all, which is a struct, and that has some filler variable here taking up 6 bytes, so that the next member of our struct, which we can call marker opcode of the type unsigned int 8, directly aligns with byte 6 in our bytes array. And another member CRC, again unsigned integer 8, which aligns to byte 7. And we do the same with the NOP member here. We just need 2 filler variables here, taking up 16 bits here and 16 bits here. And then we can, in the middle, have an unsigned integer 16 variable, which we call key, which aligns beautifully with bytes 2 and 3 and can be directly accessed as 16-bit integer. Of course, we can do the same with the MISO messages, creating a union MISO message, which handles all that jazz here, again in addition to a byte array. Here are these 2 unions in the actual code in the definition of the class, still the private part. So we have here our union MOSI message, which has as a first member an array of bytes with message size. Message size is just a constant I defined. It's 8, of course. Then we have here a struct all for the member all, which first has a byte array with varying content. We don't know what that is in general, but it's the message size minus 2 bytes. So 6 bytes to align the next 8-bit member marker opcode and then the last member also 8-bit CRC. And we have an additional struct knob here for the member knob, which starts with a 16-bit unsigned integer unused. So our 16-bit unsigned integer key is probably properly aligned to our byte array, and at the end we have another integer 16-bit unused too. The union for the MISO messages works exactly the same. We start with our byte array, then we have a struct all for the member all with here that dummy variable, this time 7 bytes, to align our CRC to the last byte of our byte array. Struct other for the member other, again varying content in the first 6 bytes, and then follows the 8-bit marker opcode and the struct knob for the member knob. Again, first 16 bits unused, then 16 bits for the key echo and another 16-bit for the inverted key echo. With all these preparations, coupling together an actual knob message to send it becomes quite easy. Here we have the public method sendKnob, which gets as an argument an unsigned 16-bit integer key. Optional, it defaults to 0. Then we have a local variable, our union MOSI message. And then we simply say, okay, MOSI message is a knob and unused 1. The first 16-bit should be initialized to 0. Somewhere in the datasheet it says you should set unused bits to 0 in the messages, okay? And the key in our knob message becomes simply our argument key. And we also initialize the last 16 bits unused 2 also to 0. And then we switch over to the all member, so no redundancy here, and set the marker opcode to the 2 most significant bits to the marker other, and exclusively all that with the MOSI opcode for knob. And then we pass the whole MOSI message, which is finished, to a method send. We will talk about that later. That can return a Boolean yes or no, if it's successful or not. And this is also passed back here by our method to indicate if it was successful or not. The coding messages we received from our slave becomes this way also quite easy. I have here, for example, the public class method last knob echo key, which should hopefully return the echo key in a knob message. MISO message is just a private class variable of the type union MISO message. And that, as we saw, contains a knob struct, and from that knob struct we just return the echo key here, and we're done. Same for last knob inverted echo key, but instead we return the struct member inverted key echo. Let's go over the remaining code real quick. There's nothing new, nothing we haven't done before. So in the .h file of the class, we have the usual if not def define statements here with a class macro just to prevent the class definition being included twice or thrice. The related and if is of course at the end of the file. We include spi.h because we're using SPI, and then we have our class definition, the public part. And there we define first an enum class library error, currently an unsigned integer 8, and we only have 2 errors at the moment. We will see where they are thrown, a CRC error and an opcode error. The default constructor is not valid, so it's deleted, and then we have here the real constructor for the class. We will talk about that in detail when we have a look at the CPP file. Then we have a begin method, which should be called after you called the SPI begin. Details again when we look at the CPP file. We already talked about the Boolean send knob with the key argument method in detail. Then we have also the last knob echo key and the last knob inverted echo key. We also covered that already. Finally, we have the last library error method, which returns the last library error. Again, details when we look at the CPP file. And then we are already in the private part of the class. We first have 2 static const expressions here. Unsigned int 32-bit, the SPI max speed of 2 MHz. According to the datasheet, that's the maximum SPI speed that the MLX90363 can handle. And we talked about that the message size, we saw that before, which is 8 bytes. We already talked about the enum class marker, the enum class MOSI opcode, and the enum class MISO opcode. We also already covered the typedef union MOSI message and the typedef union MISO message. That leaves us with just 5 private class variables. We first here have a reference SPI to the SPI to an SPI class object. That's of course used to store the SPI object we are using. We have here an unsigned integer 8 where we store the SPI SS pin for addressing our slave and the actual SPI speed we are using. We have here, we saw that already in use, that variable MISO message, which just holds the last received MISO message, and last library error, which holds the last library error that occurred. Finally, we have 2 private functions here. CRC, we already had a look at that, and then at the core, of course, a send method, which we will have again a look when we switch over to the CPP file, which we will do now. Please note the and if at the end of the .h file. And here's the CPP file of the class. Of course, we first include our .h file. And then we have here our constructor with 3 arguments, the SPI object we want to use, the SS pin we want to use, and optionally the SPI speed we want to use, which defaults of course to the constant SPI speed max for the chip. And we just initialize one-to-one our private class variables with the parameters we passed. Then the begin method. Currently not much happening here. We switch the pin mode of our slave select pin to output, and we set that slave select pin to high, disabling our slave. We already had a look at the send knob method in detail. So next is the last library error method, which returns a library error, and it just returns the last library error private class variable. We already covered the last knob echo key and the last knob inverted echo key methods. as well as our CRC method. That leaves us with the private send method, which gets as an argument a MOSI message as a C++ MOSI message in num, and it returns a bool, a true for successful, false for some error occurred. We have here a local variable, unsigned integer 8, I for a loop. And first we calculate here the CRC byte within our MOSI message using our CRC method from the 8-bit byte array within our MOSI message. Then we simply do an SPI begin transaction with the following SPI settings. Yeah, our SPI speed, which we can either set through the constructor or it defaults to the maximum SPI speed. It's MSB first communication, so most significant bit first in every byte, and SPI mode is 1. Both is very well documented in the datasheet. Then we do a digital write to our slave select pin to low to address our slave, and then we go through the 8 bytes of our message, and for every byte we do an SPI transfer of our MOSI message byte, and we write the received byte from the slave into our MISO message byte. Then, slave select pin back to high, deselect our slave, and an SPI end transaction. And now we check if in our MISO message all CRC, the CRC is identical to the CRC we can calculate for all the first 7 bytes in our MISO message. And if that's not the case, we raise an CRC error and return false. Then we finally check if the MISO message other marker opcode is equal to the only one marker opcode combination we already know, and that would be the marker other binary odd with the MISO opcode knob. And if that's not the case, we raise an library error opcode, unknown opcode, okay? And also return false, otherwise we return true and we're done. Not much to tell about the sketch. We include our class.h file. We have here a constant byte, the slave select pin, which is 10. We saw that in the basics video. We create here an object of our class. As parameter, we pass the standard Arduino SPI object and our slave select pin. We don't pass the speed. We are happy with the 2 MHz maximum default. In the setup, we do a serial begin and we wait until serial is ready. Then we do an SPI begin before we do an MLX90363 begin. And then comes the loop. We execute a send knob with a certain bit pattern here. So 16-bit, 01, 01, 01, etc. And if that fails, we do a switch over the last library error, and if the last library error was a CRC, we print on the serial port a CRC error. Otherwise, if it's an opcode error, we print opcode error on the serial. Otherwise, we print on the serial knob echo key, and please note I OR here, binary OR here, the last knob echo key with this binary 17-bit constant, so I always have a 1 at the beginning. So we can ignore later in the serial monitor the most significant bit. That's just for formatting reasons. And I do the same for the inverted echo key. Then I wait for 500 milliseconds and we start again. That's it. And here's the output on the serial monitor. Boring. So knob echo key, yeah, ignore the 17th bit here. That's the 10101 bit pattern that we passed when we sent the knob command. And the inverted echo key, again, ignore that 17th bit, 010101, etc. However, have a look at that. I think I saw an error pop up just when I freshly connected that thing. So let's do that again, plugging it in and opening the serial monitor. And okay, something interesting happening here. We have an opcode error. Yeah, something to be handled in the next video. That's it for today. I guess we have a reasonably nice framework now for our little chip, which we can build on. I told you in the beginning, this will be a boring video, just laying the basics here and coming up with a elegant and efficient framework. I guess next time, we will handle that error, definitely, meaning we will probably implement more OpCodes, and maybe we are even implementing the OpCodes for a regular message, okay, so we can get actually some magnetic data back from our chip. Till then, bye.